Welcome. In this session, we'll summarize and slightly generalize what we've explored in the previous sessions of this lecture. We'll look at what we'll call a basic quadratic problem, and this is a problem that has a quadratic objective and linear equality constraints. What we want to do is we want to solve an optimization problem subject to some constraints, and in particular, what we want to have is a quadratic objective. So that means it's a quadratic form plus a linear form. Here the linear form, this Q vector that we're transposing could be 0, and this matrix has to be symmetric, positive, semi-definite. That is, there might be some 0 eigenvalues, but all of the other eigenvalues have to be positive, and there has to be at least one positive eigenvalue for it to be symmetric, positive, semi-definite. The property functions that we'll explore here are linear. That is, they're a matrix times the vector argument minus a constraint vector. What we'll do is when we perform the differentiation, the transposition, setting it equal to 0 vectors and rearranging, is we get a general linear equation like this. So this, because the matrix is symmetric, in the derivation it will be K transpose, but we can just rewrite that as K. The off diagonal are the constraint, the linear constraint matrix and its transpose. This is always a 0. If there's just one property, it'll be a 0 scalar, otherwise it's a 0 matrix. This is the argument, and it's the optimal argument that we'll be finding. This is one or more Lagrange multipliers, and here is the Q vector that comes out of the linear form of the quadratic equation, and this is the constraint vector. A numerical problem is that the matrix we're looking at is indefinite, and specifically the positive eigenvalues and any 0 eigenvalues are coming from that matrix K in the quadratic form of the quadratic equation, and the negative eigenvalues are coming from M. So we always have some positive values, we always have some negative eigenvalues, and that makes this numerically challenging to solve as the size of the system increases. So in summary, what we've discovered is that when we solve these equality constraints using Lagrange multipliers, what we're doing is we're adding variables. We have the number of variables that come from the size of the vector space for the vector argument, and then we're adding a Lagrange multiplier for every constraint property that we have. Here we're using equality constraints. These lead, when we differentiate them, they lead to first order constraints, and then specifically, if our properties are linear equalities, then what we end up with is a large linear equation.